Welcome back, everyone. We've got another deep dive ready to go, and this time it's all about a paper that caught your eye, carbon dioxide capture from open air using covalent organic frameworks.
Catchy title, huh?
You got it.
Yeah.
But really, we're honing in on this material they're calling COF-999 and its potential for, well, saving the planet kind of stuff.
Sounds a little dramatic.
Yeah, fair enough. But capturing CO2 directly from the air is a pretty big deal, right? Like in the fight against climate change.
Absolutely.
And we'll also be looking at this other paper, development of zeolite adsorbents for CO2 separation in achieving carbon neutrality.
Right.
Just to kind of give us some context and compare COF-999 with those zeolites, because they're also being used for CO2 capture.
Yeah.
But first things first, why is capturing CO2 from the air such a big deal anyway? It's not just about reducing emissions at the source, is it?
No, it's about tackling what's already out there. Even if we stopped emitting CO2 tomorrow, we'd still need to remove the CO2 that's already up there. It's like we've overfilled the bathtub.
Oh, I like that.
Turning off the tap won't drain the tub, right? We need to actively scoop out some of that water, and that's what direct air capture, or DOC, is all about.
Okay, that makes sense. But we already have methods for DOC, so what makes this COF-999 stand out? What's so special about it?
It's all about efficiency and durability. Existing methods are like those old, clunky vacuum cleaners. They kind of work, but guzzle energy and can be a bit messy. Some use liquid solutions that require a ton of energy to regenerate. And then there are those that use materials that break down over time or get clogged with water.
So COF-999 is like the sleek, new Dyson of CO2 capture, efficient and built to last.
You got it. That's the idea. The researchers really thought outside the box to overcome those limitations. It's a covalent organic framework, essentially a network of strong, interconnected molecules with tons of tiny pores.
Okay, so I'm picturing this super spongy material with all these little pockets for trapping CO2. But how does it actually work? Does it just suck the CO2 in like a vacuum cleaner?
It's a bit more nuanced than that. First, those pores are hydrophobic, meaning they repel water.
So it's like a raincoat for the COF, keeping it dry.
Exactly. No soggy sponges here. This keeps those pores free for CO2 capture and maximizes the space for grabbing those CO2 molecules. And to tackle the breakdown issue, they attach things called polyamines directly within the pores.
Wait, polyamines, that rings a bell. Aren't those like those tiny molecular claws we talked about in a previous deep dive? The ones that grab onto CO2?
You remember. And because they're chemically bound, they won't leach out over time. They stay put and ready to grab more CO2.
That's pretty neat. So how much CO2 can this COF-999 actually capture? Do we have any numbers?
In lab tests, it captured 0.96 millimole of CO2 per gram of material under dry conditions. But under 50% relative humidity, which is more realistic, like outdoors, it captured 2.05 millimole per gram.
Wow, that's a big jump. So it actually works better in humid conditions. I wouldn't have guessed that.
Right. You'd think water would be a problem, but no. And remember, low water uptake means easier regeneration. It works perfectly at just 60 degrees Celsius.
So less energy needed to reset the material for another round of CO2 capture. That's a huge win for sustainability.
But did they just test it in the lab, or did they take it outside for a real-world test?
They actually did both. To prove its real-world potential, they took COF-999 to Berkeley, California for some open-air testing. They put it through over 100 adsorption-desorption cycles for 20 days straight. Imagine that.
Wow, that sounds pretty intense. How did it hold up? Did it survive?
COF-999 aced the test. It maintained its performance throughout those 100 cycles, and they even checked for any structural changes afterwards.
To make sure it wasn't falling apart, right?
Exactly, and guess what? No changes whatsoever.
Okay, color me impressed. This COF-999 sounds pretty amazing. But I'm still a bit fuzzy on how those polyamine chains actually work. Like, what's the chemistry behind it all? How do they grab onto the CO2?
It's all about those electrons. The polyamines have nitrogen atoms with these lone pairs of electrons, which are basically negatively charged and, well, opposites attract right.
Ah, basic chemistry. So where's the positive charge in this equation? The carbon atom in the CO2 molecule has a slight positive charge. So when the CO2 enters the pore, those negatively charged electrons on the polyamine go in for the grab.
So it's like a molecular handshake.
Exactly. And they form this bond called a cardamate.
So they hold on to each other tight. But we don't want the CO2 to stay trapped forever.
Of course not. That's the beauty of this. It's reversible. By applying a bit of heat or changing the pressure, we can break that bond and release the captured CO2.
Ah, so it's a catch and release system. But you mentioned something about water playing a surprising role in all of this.
Yes. You'd think water would be a problem, competing for those binding sites. But a small amount of water actually enhances CO2 capture. It stabilizes those carbamate structures.
So the water's actually helping the CO2 get trapped more effectively. That's crazy.
Right. It's not always as simple as we might think. Sometimes a little water can be a good thing.
This is fascinating stuff. But let's zoom out
are
of the
the
potential implications of this research for the bigger picture of climate change.
That's the exciting part. It's still early days for COF-999, but its performance and durability have opened up some really exciting possibilities. Imagine massive installations equipped with COF-999 strategically placed around the globe, acting like giant air filters.
Like those massive air purifiers people use for allergies, but for the entire planet.
Exactly. They could help us draw down that excess CO2 that's already in the atmosphere, giving us a fighting chance against climate change.
That's an incredible vision. What else could we do with all that captured CO2?
Instead of just storing it, we could use it as a feedstock for producing valuable products. Imagine using CO2 to make synthetic fuels, building materials, plastics, even fertilizers.
Hold on. So we could turn CO2, the climate villain, into a valuable resource.
Exactly. It's called carbon capture and utilization, or CCU, turning a problem into a solution.
I love that idea. Okay, I'm starting to see why you're so excited about this COF-999. It really does seem like a breakthrough. But let's be realistic. What are the next steps? What needs to happen to make this a reality?
Well, scalability is a big one. Right now, the synthesis of COF-999 is a bit complex and time-consuming. We need to figure out how to produce it on a large scale at a reasonable cost.
Right, lab scale success is one thing, but mass production is a whole other ballgame.
Exactly. And we also need more long-term performance testing. While that 100-cycle test in open air is promising, we need to see how it performs over thousands, maybe even millions, of cycles in different environments.
So proving its robustness and reliability in the long run makes sense. But for now, COF-999 is definitely something to watch. Now let's shift gears a bit and talk about those zeolites.
Sounds good. They've been around for a while, so let's see how they measure up against this new kid on the block.
All right, let's dive into the world of zeolites.
All right, so zeolites. You wanted to know how they stack up against COF-999 for capturing CO2.
Exactly. I mean, COF-999 seems pretty impressive, especially with how well it performs in humid conditions and that low regeneration temperature. But zeolites have been around for ages. I'm guessing they wouldn't still be around if they weren't good at their job.
Good point. Zeolites are like the veterans of CO2 capture.
Yeah.
They've been studied for decades and were already used in a bunch of industrial processes.
So they have a proven track record. But how do they actually capture the CO2? Do they have those same polyamine claws as COF-999?
Not quite. Their structure is key here. Think of a honeycomb,
Okay.
but like on a molecular scale,
Okay.
zeolites have these intricate networks of tiny pores and channels.
I'm picturing a microscopic sponge with all these tiny tunnels running through it. And those tunnels are what trap the CO2.
You got it. It's called physisorption.
Physisorption. That sounds a bit different from that chemical handshake we talked about with COF-999.
It is different. Physisorption is more of a gentle attraction between the CO2 molecules and the zeolite surface. Like, think about a magnet attracting a paperclip.
Okay.
It's not a super strong bond, but it's enough to hold the CO2 in place.
Okay, so it's more of a gentle hold than a firm grip. But doesn't that mean they're not as effective at capturing CO2?
Not necessarily. They can be incredibly efficient, especially if they're designed for specific CO2 capture situations. Remember that paper about optimizing zeolites?
Yeah.
It mentioned something about the Sial ratio.
Right. What was that all about?
Well, that's one of the ways researchers can fine-tune those zeolites for CO2 capture. The Sial ratio is basically the balance between silicon and aluminum atoms in the zeolite structure.
So it's like adjusting the recipe for making the zeolite using different amounts of silicon and aluminum?
Exactly.
But why did that affect how well it captures CO2?
Well, those aluminum atoms, they bring negative charges into the framework. And those negative charges can interact with the slightly positive carbon atom in CO2.
Ah, so a zeolite with more aluminum will be stickier for CO2.
Exactly. And they also play around with the size and shape of those zeolite pores.
Right, like making sure they're just the right size to let CO2 in but keep other molecules out, like a bouncer for the zeolite.
Exactly. It's like creating a custom-fit sieve for CO2. And sometimes researchers combine these strategies, to make even more selective and efficient zeolites. It's pretty amazing.
Okay, so we have these optimized zeolites, but how do they compare to COF-999? Which one comes out on top?
It's not really a competition. It's more about understanding the strengths and weaknesses of each material. For instance, COF-999 shines in humid conditions and needs less energy for regeneration.
Yeah, that was pretty clear from those open-air tests in Berkeley.
Exactly. But zeolites have a long history of being used in various industrial applications. Plus, some types of zeolites are super efficient at separating CO2 from other gases, even better than COF-999.
Okay, so COF-999 is like the new kid on the block with some impressive skills, especially in those humid environments. And zeolites are the seasoned pros with a proven track record.
That's a great way to put it. It really depends on the specific situation and conditions.
Makes sense. You mentioned some types of zeolites are particularly good at separating CO2 from other gases. Are there any specific ones that stand out?
There are a few. Zeolite 13X, for instance. It's got a high CO2 adsorption capacity, especially at low pressures.
So it's like the workhorse of the zeolite family.
Yeah. And it's also cheap and readily available, which is a big plus for using it on a large scale.
Okay, what about others? Are there any more zeolite stars out there?
There's also Nauka. It's really good at picking out CO2, even from nitrogen, which is pretty cool.
So it's very selective.
Yeah, it's like a gatekeeper, letting only CO2 through. That's super useful for purifying CO2 from those gas mixtures.
Okay, I'm starting to see how diverse these zeolites are. They're not all the same. But let's go back to water for a second. We talked about how a little bit of moisture actually helps COF-999.
Right.
But what about zeolites? Are they as water-friendly?
Not really. Water can actually be a problem for zeolites when it comes to CO2 capture.
Really? Why is that? I thought water makes things sticky.
Well, it can, but many zeolites are hydrophilic.
Maybe.
They love water.
Okay.
And that can be a problem because water can actually clog those tiny pores, blocking the CO2 from getting in.
So the pores get flooded, and there's no room for the CO2.
Exactly. And this is especially true for zeolites with smaller pores. They get saturated with water really quickly.
So it's a case of water bad for zeolites.
Pretty much. But researchers are always looking for ways to improve things.
Like what?
Well, they try to modify the zeolite surface to make it more hydrophobic, like adding a water repellent coating.
Ah, so giving the zeolite its own raincoat.
Exactly. And they also design zeolites with different pore sizes.
Like those hierarchical pore structures we talked about, right? With the micropores and mesopores, like a well-organized transportation system.
You got it. The bigger pores can handle some water without blocking those smaller pores where the CO2 capture happens. It's all about balance.
Okay, that makes sense. Now, we've talked a lot about capturing CO2, but what about releasing it? How do we get it out of those materials?
Well, both COF-999 and zeolites can be regenerated using temperature or pressure swings.
Can you remind me what those are?
Sure. A temperature swing basically means heating up the material to break those bonds holding the CO2.
So we're baking the CO2 out.
Yeah, something like that. And a pressure swing means lowering the pressure around the material. It's like creating a vacuum that sucks the CO2 out.
Okay, both methods sound pretty straightforward, but is one more energy efficient than the other?
That's a really important consideration, and COF-999 might have the upper hand here. Remember those hydrophobic pores?
Yeah.
They actually reduce the energy needed for regeneration because there's less water to heat up.
Those water-repellent pores really come in handy.
They do, and COF-999 has shown good results with regeneration at just 60 degrees Celsius.
That's pretty impressive. How do zeolites compare?
They usually need higher temperatures for regeneration, but researchers are always working on new and improved zeolites, so who knows?
It's like a friendly competition to see who can be the best.
Exactly, and that's how innovation happens.
All right, so we've captured the CO2 and released it. Now the question is, what do we do with it all? We can't just release it back into the atmosphere, can we?
Definitely not. There are a few options. One is geological storage.
I've heard of that. Remind me what that is.
We inject the CO2 deep underground into those stable rock formations, like old oil and gas reservoirs or saline aquifers.
So we're putting it back where it came from, but in a safe way.
Exactly. Those formations can hold a lot of CO2 for a really long time, taking it out of the carbon cycle for good.
Okay, and the other option?
Carbon capture and utilization, or CCU. It's about using that CO2 to make useful things.
Wait, we can actually turn CO2 into something useful? Like what?
Lots of things. We can make synthetic fuels, building materials, even plastics and fertilizer.
That's incredible, turning a problem into a resource.
Precisely.
Yeah.
It's a really exciting area of research.
Okay, so we can either store it safely or use it to make valuable products.
Yeah.
That's great. But I imagine there are some ethical and societal things to consider too, right?
Absolutely. Like any technology, we have to think about the potential risks and unintended consequences.
Like what?
Well, some people might get complacent about reducing emissions if they think we can just capture it all, you know?
Oh, so it's important to make sure that CO2 capture doesn't become a crutch.
Right. It's
Yeah.
not an excuse to keep polluting. It should be part of a bigger strategy that prioritizes reducing emissions.
I see. So it has to be part of a holistic approach.
Exactly. And we also have to think about the potential environmental impact of capturing and storing all that CO2. We need to make sure it's done safely and responsibly.
So that our solutions aren't causing more problems down the line.
Exactly. We need to be careful and think things through.
This has been an amazing deep dive. I've learned so much about COF-999 and the whole world of CO2 capture. It's amazing to see how scientists are coming up with solutions to these challenges.
I agree. It's really exciting to see these advancements, and who knows what the future holds.
I'm definitely feeling more optimistic about the future after this. And thanks again for joining me and sharing your expertise.
My pleasure.
Now, in our final part, we'll zoom out a bit more and look at the bigger picture of CO2 capture and its role in tackling climate change.
Sounds good. Let's broaden our perspective a bit more.
All right, so we've talked about COF-999 and zeolites and all these amazing materials that can grab CO2 right out of the air.
We've even touched on some of those bio-inspired approaches.
Right, but now it's time to zoom out and look at the bigger picture. Like, how does all this fit into our fight against climate change?
Well, it's important to remember that CO2 capture is just one tool in our toolbox.
Not the whole solution, right?
Exactly. It's not like we can just keep emitting CO2 and expect these technologies to magically clean up our mess.
So no free pass to keep our carbon-intensive lifestyles.
Definitely not. It's like having a cleaning crew. They can tidy up,
Yeah,
but it's still better not to make a mess in the first place, right?
makes sense. So we can't forget about reducing emissions at the source.
Absolutely. We need to transition to renewable energy, improve energy efficiency, and basically just adopt more sustainable practices in everything we do.
Got it. It's a multi-pronged approach.
Exactly. And CO2 capture technologies, while promising, they need to be part of a broader strategy. They're a tool, not a replacement for making real changes.
Okay, that makes sense. So even if we scale up these technologies and capture tons of CO2, what do we do with it all?
That's a great question. We can't just capture it and let it sit around. We need to figure out what to do with it.
We talked about geological storage, right?
Yeah.
And carbon capture and utilization.
Right. Geological storage is basically putting the CO2 back underground, like in those old oil and gas reservoirs or saline aquifers.
Well, tucking it away safely.
Yeah. And those formations can hold vast amounts of CO2 for a really long time. And then CCU, that's all about using that CO2 to create something useful, like synthetic fuels, building materials, plastics, even fertilizer.
Turning a climate villain into a valuable resource.
Exactly. It's a super exciting area of research, and I think we'll see even more innovative uses for CO2 in the future.
It's amazing to think that something that's causing so much harm can be turned into something beneficial.
Absolutely. But with any new technology, we need to be mindful of the potential downsides.
What kind of downsides are we talking about?
Well, for one, having these CO2 capture technologies could lead to complacency. People might think, oh, we can just capture all the CO2, so it's okay to keep emitting it.
Right, it's important that we don't use it as an excuse to keep polluting.
Exactly. We can't lose sight of the ultimate goal, reducing emissions. CO2 capture is a tool to help us get there, not a way to avoid making tough choices.
And what about the environmental impact of capturing and storing all that CO2?
That's another important consideration. We need to do it carefully, minimize the risks of leaks, and make sure it's done in an environmentally responsible way.
So it's about finding the right balance between solving one problem without creating new ones.
Exactly. It's a complex issue with no easy answers, but the research and innovation in this field are really inspiring.
It's definitely been an eye-opening journey. I've learned so much about COF-999, zeolites, and the whole world of CO2 capture. It's amazing to see how science is tackling these huge challenges head on.
I agree. And the best part is, it's not just scientists and engineers working on this. We all have a role to play in creating a more sustainable future.
Absolutely. So to our listeners out there, keep learning, stay curious, and let's all do our part to make a difference. Thanks for joining us on this deep dive into the world of CO2 capture.
It's been a pleasure.
Until next time.